Assalamualaikum and hi. So today I would like to share with you my findings about vector in real life related to aircraft navigation. So let's start it. So first of all, I would like to introduce myself. My name is Muhammad Hanif bin Rosbi and I was born in Bachok, Kelantan. And my IC number is 06072203 and 11 and 89. My index number is 2024 08 23 10179 and my matrix number is P24 2024 08 23 and 90. So before I start my presentation of the application of vector in real life, I would like to thank our lecturer Puan Hajah Idawati binti Cik Mat for their guidance and for giving me the chance to be making this assignment and be giving a chance for me to be researching about how we conduct vector in our daily life. So let us start with our question. So before I share it with you guys my findings, first let me enlighten you what is a vector. A vector is a quantity that has both magnitude or size and direction. It is often represented as an arrow, where the length of the arrow indicates the magnitude and the direction of the arrow shows the direction of the vector. Try imagining in the simple term. Okay, you take a car. Okay, you think of the car, and you think, the car is moving to 100 kilometer per hour, but where it is moving to, where it is headed. So when there is no really direction where it is headed, you could say that the car is not moving at all. So that is the difference between scalar and vector. And so what are the examples of vector is displacement, velocity, and force, where every of the example got their own magnitude and got their direction where it is heading. So my findings are related to vector of aircraft navigation. So there is a scenario where Mr. Hanif, an experienced navigator, is on a duty to make sure a smooth flight for a commercial aircraft journey from Kuala Lumpur to Singapore. In his job desk, Mr. Hanif must account for the wind's influence on the aircraft's path to reach its destination accurately. The aircraft's airspeed is 200 km per hour due east, and the wind's velocity is 50 km per hour, blowing from the northwest 45 degrees south of east. So the question stated that we want to know how the wind influence the aircraft movement and how does it affect the accuracy of the aircraft. So this is the question that we are going to solve today. So we need to calculate how the wind influence the aircraft path. First, we need to find the eastward component of the wind. From this question, it is represented as VWX. So how do we find it? To make it easier, you can draw it separate diagram. So this is what we're going to find, and this is the given degree of the question, and this is the wind's speed. So to find eastward component of the wind, we use the trigonometry, which is cos theta equal to adjacent per hypotenuse. From here, cos theta is 45 degree equal to adjacent, what we want to find, eastward component of x component and hypotenuse is the 50 kilometer per hour, and we multiply both sides with 50, so it's going to be like this. So the final answer will be 35.36 kilometer per hour. Then let's move on to the southward component of the wind. Okay, so like previously we draw a triangle. When we look at this scenario, it is the same as what we previously calculate. So, and it's also be using the same principle as cos theta equal to adjacent, which is our what we want to find, the southward component of the wind, and the hypotenuse, which is 50. So I would theoretically say that the answer is the same, which is VWY is equal to 35.36 kilometer per hour. So let's move on to the next step. So for the next step, we need to find the resultant velocity for the eastward component of the vector and the southward component of the vector. It's just easy. It's just an addition of vector. So to get the eastward component of the resultant velocity, we just need to, or I would like to, resultant velocity represented as VR, eastward component x equal to 200 kilometer per hour plus what we calculate just now, 35.36 kilometer per hour is going to be 235 kilometer per hour. Sorry, 35.36 kilometer per hour. So as the resultant velocity of the south component is moving down, so we could say that it's going to the negative bar. So we could say that 0, since our plane is moving straight to the east, so there's nothing to the bottom, so plus negative 35.36 kilometer per hour. So it's going to be negative 5.36 kilometer per hour. So after we find the resultant velocity for eastward component and southward component, we need to find the magnitude. To find the magnitude, which is represented as VR magnitude, you can use Pythagorean theorem, such as a square plus b square equal to c square. But we can substitute the east component of the wind square plus southward component of the wind square equal to magnitude square. So it's going to be like the magnitude equal to square root 235.36 square kilometer square plus negative 35.36 square. So the answer would be approximately 238 kilometer per hour. This is for the magnitude. And lastly, we need to calculate the direction where the aircraft is heading. To make the calculation easier, we need to draw the diagram first. So, sorry, nak ayam. So, this represent the resultant velocity of eastward component. This represent our magnitude. This represent the southward of resultant velocity. As is given, we need to find the degree here. So we can use tangent. Tangent theta equal to opposite, which is the resultant velocity of south component divided by resultant velocity of the east component. So we just need to substitute the value tangent theta equal to negative 35.36 divided by 235.36. So we move the tangent to the right side. It's going to be arctan 35.36 divided by 235.36. So the final answer would be negative 8.5, which is heading south of east, which you can see right here. It's moving a little bit south of east. So the final solution of the calculation stated that the magnitude represents the aircraft ground speed, which is the actual speed over the ground, 238 km per hour. Mr. Hanif sees that the ground speed is significantly higher than the airspeed due to the wind's influence. This means that the aircraft is going to arrive earlier than expected. And secondly, the direction tells Mr. Hanif that the aircraft is heading approximately 8.5 degrees south of east. So, to keep the aircraft on track, Mr. Hanif should tell the aircraft driver to move 8.5 degrees north of east to counterback the wind's influence on the aircraft. So, in conclusion of my findings, we got to know that vectors are crucial in real-life application, especially in aviation navigation, for ensuring precise headings and ground speed. Accurate vector calculations, such as those used in Mr. Hanif's case study, highlight their importance in safe and efficient flight operation. Broader examples from other fields, for example, computer graphics, engineering, could expand understanding of vectors' versatility. So, after doing my research, I got a new ideas that I would like to suggest our government to build an AI-powered adaptive navigation system, or it could be called ANS, where it developed an advanced AI-powered system that combines real-time vector analysis with machine learning algorithms to dynamically adapt flight path in response to changing conditions. So, how does this AI work? Okay, try imagine that we are conducting an aircraft while we are conducting our aircraft, there is a sudden change of weather in our flight path. So the AI will receive the information and quickly make a calculation on new path that we could use that will coming in handy in our future, and making sure that the flight arrive at the designated location.